Hello everyone. So today let's solve the problem. This one, Starry night camping, right? So just give me a second here. 1 second. Yeah, Starry night camping, right? So this was asked in the Codeforces 2050 and Codeforces round 718. Sorry, contest 2050 and Codeforces round 718 for the division 1 as well as the division 2, right? So let's see what the question states. You can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem. Yeah. First, let's see what the question states actually in simple terms. Yeah. First, we have n tenants. Yeah. We have n tenants at integer coordinates x and y. We have n tenants at the integer coordinates x and y, each with a weight ui, each with the weight wi. Right. So this is fine. A tent is important if both xi and yi. Tent is important if both xi and yi are even. If xi and yi are even, basically if x and y are even, right? So this is fine. We must delete some tents so that no remaining important tent is the corner of a 1 into k parallelogram or the rectangle that is formed by itself, and three other tents within Chebyshev distance 1, right? Chebyshev distance 1, right? So just remember this one. Again, I'll just read this one out loud until here. Just listen to this carefully. We have n tents at the integer coordinates xi, yi, this one, x comma y, each with a weight w, right? A tent is important if both xi and yi are even. This one, x and y are even. A tent is important if both x and y are even. We must delete some tents. We must delete some tents so that no remaining important tent is the corner of 1 into k parallelogram or the rectangle formed by itself, and three other tents within Chebyshev distance 1, right? Chebyshev distance 1 points inside a 3 into 3 block. Basically, all the 4 points inside a 3 into 3 block, sorry, with one side parallel to the x-axis. So what we need to do here, what is our main thing here? We have to maximize, just remember this, we have to maximize the total weight of tents, total weight of tents kept and printed, total weight of tents kept, and we have to print this one. Yeah, we have to maximize the total weight of the tents kept as well as print. We have to print them. Yeah, so just let me read this one question loud entirely. Just listen to this carefully. So we have n tents uh, at an integer coordinates x, y, with each with a weight w. This one, yeah, a tent is important if both x and y are even. This one, if both x and y are even, right? So we must delete some tent so that no remaining important tent is the corner of 1 into k parallelogram or the rectangle formed by itself, and three other tents within Chebyshev distance 1, right? Here all the 4 points inside 3 into 3 block, all the 4 points inside 3 into 3 block. Just remember this one. Yeah, so with one side parallel to the x-axis, with one side parallel to the x-axis. Yeah, what we need to do, we have to maximize the total weight of the tents kept, and we have to print it. We have to maximize the total weight of the tents kept, and we have to print it. Yep. So let me delete this one. This is the question mainly. Yeah, so they have given n here, also the edge along with the weight. So these are the edges actually along with the weight. So they have given the edges are this one. We have the negative value as well here, right? So this one, they have given edges. This is weight 4, 5, 3, 1, 2. This is weight basically. Yeah. So this is related to the flow actually, graph flow problems, right? So flow can be of any type. Basically, matrix flow problems also exist. There are so many type of problems, right? So currently we are solving the graph basically based on the network flow, right? So this is one of the important problems, network flow problems. Yeah. So let's do one thing. We have the understanding of the question. We have the understanding of the input output as well. Let's do one thing. Let's discuss the approach followed by the complexities, and then let's write the code. As usual, let's discuss the approach first. So here, yeah, let's consider the same thing, man. Just give me a second here. Yeah, let's consider the same first example for the approach actually. Yeah. So here, as I've said before discussing the approach, let me tell you, we will be making use of the Dinix algorithm. So Dinix algorithm, we have very recently we discussed the Dinix algorithm. If you want to know the Dinix algorithm, if you don't know the Dinix algorithm basically make uses of this one DFS as well as the BFS. It uses both BFS as well as the DFS. If you don't know Dinix algorithm, please do go through the graph playlist. In the graph playlist, Dinix algorithm is mentioned along with the push relabel and other important flow algorithms. Yeah, so I can just go through the Dinix algorithm so that we understand the problem clearly, right? It will be very easier for us to solve the problem. It makes use of both DFS as well as the BFS. I'm speaking of the Dinix algorithm here, right? Again, if you don't know the Dinix algorithm, please go through the graph algorithms playlist. You will find the Dinix algorithm at the bottom, right? So you'll find the Dinix algorithm as well as the push relabel algorithm. Both are related to the this one. What do we call maximum flow? Actually, it is related to the flows. Actually, network flow in simple term. Yeah, there are so many algorithms that we discussed that relates to the or that is related to the this one maximum flow or the flows. Actually, Dinix algorithm is one of the very important problem. This one algorithm. We will be making use of the Dinix algorithm, or we will be implementing the Dinix algorithm for this particular problem. Yeah. So I hope this part is completely clear, man. Yep. So first thing here. So we will be considering this one first input or the first example. Yeah, for the approach basically. Let's move on with the first step, man. First important step. Yep. So first we will identify the parity class of each point. Yeah. First we identify the parity class of each point by x mod 2 and y mod 2. X mod 2 and y mod 2. See here. First what we do, we identify the parity class of each point by x mod 2 and y mod 2. X mod 2 and y mod 2. Yeah. So important tents are here. This one. We can just consider this one actually. 0, comma 0. Important tents are 0, comma 0 mod 2. Mod 2 basically. Yeah. 0, comma 0 mod 2. So we'll be going with important tents are, yeah, this one 0, comma 0 mod 2. So here both even, right? Here tent at 0, comma 0 weight is 4. See, this one we are considering, right? The first edge, this one tent. So the first one in the input 0, comma 0 with the weight 4. Actually, this is weight, right? So again, so 5 is number of this thing inputs we have basically, and we can consider n m anything. So here in this case, these are basically edges. First two numbers are edges here. 0, 0 edges, 0, 1 edge, 1, 0 edge, 1, 1 edge, minus 1 and 1. We have the negative value as well. Minus 1, 1. This is edge. The last number that they have provided in the input is nothing but the weight. We know this one. Yeah. So this one 0, comma 0. Both are even here. Here at the tent 0, comma 0. We have weight 4. That is very important, right? So just consider this one until here. This is the first step. Yeah. Next, let's move on with the second step, man. So listen to this carefully. So this is nothing but the we'll be considering the forbidden configuration. When I say forbidden configuration for any important tent, yeah, for any important tent, this one when both coordinates are even. So here in this case we have considered 0, comma 0, which we will consider both as even itself, right? So for the forbidden configuration, whatever we are considering here, so for any important tent, both the coordinates has to be even at any cost. If there exist three other tents actually nearby within plus or minus 1 on each axis, that together with it make a parallelogram. That together with it make a parallelogram. Just listen to this carefully, whatever I'm saying. This is very important. The forbidden configuration we are speaking of, right? For any important tent, when both the coordinates are even. So this is very important. Both coordinates has to be this one we are considering. Both coordinates has to be this one even. If there exist three other tents nearby within plus or minus 1 on each axis, that together with it makes a parallelogram. That together with it makes a parallelogram whose side is parallel to the x-axis. Whose side is parallel to the x-axis. Then that important tent must not remain simultaneously with those three equivalent, right? With those three equivalently, we must break such four tuples. Equivalently, we must break such four tuples. Yeah. So this is very important part. This is very important part. Yeah. So now let's move on with the third point. We have the understanding, right? The forbidden configuration, whatever we discussed, we have the understanding on that. Now let's move on with the third main point here. So after breaking such four tuples, we will model this as maximum weight. We will model this as maximum weight uh, uh, subset problem that can be solved by minimum cut or the maximum flow. Yeah, that can be solved by minimum cut or it can be solved by maximum flow. We are going with a maximum flow, right? In this case, we will be going with a maximum flow. That is the reason we are opting to solve with the Dinix algorithm. Yeah. So we will be modeling this as maximum weight subset problem that can be solved by the minimum cut or the maximum flow. That is the reason we'll be going with a Dinix algorithm, maximum flow problem. One of the most important algorithms this one we make use of to solve the maximum flow is one of them is this one Dinix, right? So there are many problem this one algorithms. Dinix is one of the this one Dinix algorithm is one of the most this one loved algorithms actually in simple terms. Yeah. So we'll be making use of Dinix algorithm itself. What we will do here, just listen to this carefully. We will create a bipartite like flow graph. What we will do, we will create a bipartite graph, right? We will create a bipartite like flow graph by using the parity classes. By using the parity classes. Yeah, remember this. Yeah, this is very important. Yeah, this is very important. So here, remember this, we will create a bipartite like flow graph by using the parity classes. Here we'll be making use of the four residues of x mod 2 and y mod 2, right? Yeah, we will be making use of four this one residues. I'll just write R here, four residues, this one, the terms x mod 2 as well as the y mod 2, y mod 2. Yeah, this is fine, I believe. Yep. Now we will split each node into in or out with capacity that is equivalent to its weight. We will split each node into in or out with a capacity that is equivalent to its weight. We will be adding infinite capacity edges between certain parity transitions that represent forbidden adjacency. That represent forbidden adjacency. That is what we discussed earlier. The forbidden configuration. That is the reason I said the title, the forbidden configuration. Yeah, we'll split each node into in or out with a capacity that is equivalent to its weight. Capacity that is equivalent to its weight here, right? Capacity that is equivalent to its weight, right? So we will add the infinite capacity edges between the certain parity transitions that represent forbidden adjacency. That would create the parallelogram. So we have to create the parallelogram as per the question, right? Then maximum keep is equivalent to the total weights minus min cut. So this, remember this one, we'll be making use of it. Maximum keep will be equivalent to the total weight minus min cut. I'll just write MC. MC is nothing but the minimum cut. Yeah, this TW is nothing but the total weight. Then the maximum keep is equivalent to the this one total weights minus min cut. So we will be making use of this one. Just remember this. This is very important. Yeah. So now let's do one thing. Let's try to implement the same thing whatever we have discussed till now. The same thing for the example one, for the on the example one, or by considering first example. Yeah. Let me remove this one. I hope till here everything is clear, man. So we will be considering this as maximum flow and we'll be solving this one with the this one Dinix algorithm, and other stuff that we have discussed, the same thing will be implementing on the by considering the first example. Yeah. So now for example one, this one I'm speaking of, this one flow or graph that we are considering, right? Flow or graph here construction, flow or graph construction finds a min cut of weight 3. Min cut of weight 3. How it is weight 3 here? The minimum total weight that must be removed to break all the bad parallelograms. So the answer is sum of weights that previously we had discussed, right? Sum of weights is equivalent to the 15 minus 3. Here in this case it will be 15 minus 3, we will get 12. We'll get 12 actually. So the output that we got here, the previous point if you remember, right? The previous point if you remember, maximum keep will be equivalent to the total weights minus this one min cut, right? So total weights here is 15 and the minimum cut is here 3. For the example one, the flow graph construction finds the minimum cut of weight 3. I have said that one, this one, what do we call? Um, for example one, the flow or graph construction finds a minimum cut of weight 3. I have said, right? So the minimum total weight that can be removed to break all the bad parallelograms. So answer would be here this one, total this one weights minus min cut. Total weights is 15 and min cut here is 3 as discussed earlier, right? So 15 minus 3 will give us the output 12. So the output that we got here is 12, which is equivalent to the output that they have mentioned for the example one within the question, right? So our approach works absolutely correct here. Our approach works absolutely correct here, right? So as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities. So I insist you to do the same thing, whatever I have said, right, or whatever I have showed. I insist you to try out by considering the second example so that you understand the question or you understand this one. Yeah, question itself basically or the approach correctly. You understand the question or the approach correctly, right? So your intuition may be better than mine. Who knows, right? Just try to implement the same thing, or if you want to implement in a different thing, if you have got better idea when listening to the approach of mine, you can just go with that as well. Yeah, so this is fine. Now as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would lead to because of this one, what do we call, because of e root v, e square root of v. See here, uh, for the time complexity, we are going with the Dinix algorithm. Dinix on the constructed graph runs in about because of this one, what do we call, edges square root v, right? So this is nothing but the vertex, right? This is nothing but the vertex. We know this one. We have the idea on the Dinix algorithm. Yeah. So if you don't know Dinix algorithm, again, I'm saying we have discussed the Dinix algorithm within the graph based algorithms playlist. You can just go and check there. So the programming language used is Python, but the explanation remains same. Yeah, whatever programming language you are making use of, it doesn't matter, but the explanation remains same. You can just go and watch that video and come so that you understand the problem better, right? It uses DFS and BFS both. That also I have said. Yeah. So now time complexity, we are going with the Dinix algorithm. Dinix on this constructed graph runs in about big O of e square root v in practice with utmost big O of n square adjacent checks, with utmost big O of n square adjacency checks, but only edges added for the distance one neighbors, distance minus one neighbors, right? The practical complexity, we can just write it in this way, big O of n to the power of 1.5, big O of n to the power of 1.5 for the flow, plus we can just go with big of n square for the adjacency loop. We will be making use of the adjacency loop as well. Yeah, overall it is dominated by, we can just write it in this way, big of n square plus dinic, big of n square plus dinic here, right? So the time complexity for the code that we'll be writing will be this one, big of n square plus dinic. So what will be the space complexity here? The space complexity would lead to big of n plus m. The space complexity would lead to big of n plus m. That is almost equivalent to, big of n square, man. We can just consider here n square in the worst case due to the edge arrays and node split representation. Let's consider n square itself. Yeah. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n square plus dinic and big of n square respectively. As we have complete knowledge on this one approach as well as the complexities, we are good to write the code. Let's start writing the code. Yeah. So first we'll be making use of this one, what we call fast input and the fast output. So let's do one thing. I'll just come to the compiler here. Let's import this one, input output package. This is fine. Also, we'll be making use of the different utilities. Let's import different this one utility package as well. Yeah, so this is fine. Now let's make use of the class actually. uh I'll just go with a class name main. You can just go with any class name that's relevant to the question. Yep. So within the main class, let's go with the initialization part first, right? Yeah, first let's go with the n, nothing but the max node array list that we have to consider. Also let's go with the e, nothing but the estimated max edges. Let's initialize these two first. I'll just go with here static final. So this one int n equals, let me go with 2005, as well as e equals this one int of this one, what do we call, 1e6. This is fine. The next part would be static. So this one will be final long o. So this one will be o equals. So let me make use of the long here, right? So long 1e15 here, nothing but 10 to the power of 15, right? So we are just going with o with a very large number that is used as infinite capacity. Yeah, this is fine, man. Next part is let's initialize NST as well as the total. N is nothing but the number of tents. S is nothing but the this one source index. T is nothing but the sync index along with the total initialized to 1. So let's do this one as well. Static here int N S as well as this one T, and let me initialize total equals 1 as well. Yep. Let's initialize some more things. Let's go with the arrays to store point coordinates and the weights as well. So this is one index. Just remember this one. Yeah. So this is important. I'll just go with static here int x equals new int of. So I'll just go with, let me pass n here. Big N actually. This is fine. Hmm, n itself we have considered, right? So this one we are passing size n actually. This is y. Y equals. So let me go with new int here of again big N. Next, let me go with weights here. This one equals new int of again capital N. This is fine, I believe. Next, let's do one thing. Let's go with the let's initialize or let's go with the adjacency list for the flow graph that is stored in the edge arrays. Nothing but forward star, right? Forward star. So let me go with here static. So int. So this one is head equals new int of n. This is fine. And let me go with 2 equals new int of what should I do here? New int of e. This is also fine. And next, let me go with here new int of this one, capital E. This is also fine, I believe. Next, let's go with the edge capacities, EW, right? This is long because we can consider up to 1e15 we have considered, right? So I think 1e15, 10 to the power of 15 itself, actually, in my opinion. 1e9 actually, not 1e15, sorry. So this is 10 to the power of 9. So let me write, so we have to assign this one, right? So this will be long as I've said. So I'll just go with your static long edge weights EW equals new long of. So let me pass capital E here. So this is fine, I believe. Next, let's go with the BFS and DFS helper arrays for the DINIC. As I've said, again I'll repeat the same thing here. So we will be making use of BFS as well as the DFS. So DINIC's algorithm uses BFS and DFS. This one I have stressed this one, right? So let's make use of the BFS and the DFS helper arrays for the DINIC, right? So this one I'll just go with static int array. This is fine. Dependency. So DEP I'll just go with new int of, let me pass the capital N here, size N, right? Also for the DFS we have considered. Now we have to consider for the BFS as well. First BFS, let's consider the second one DFS. So now equals. So let me go with new int of capital N. This is fine, man. Now let's do one thing. Let's go with a low level add of directed edge to the adjacency arrays. So we'll not be going with reverse. This will be used internally itself. Yep. So let me go with here static void add. We are going with the add helper method here. So this one will be int u. The parameters will be going with this one, u and v as nodes and w as weight. Yeah. So we need actually 2 nodes and 1 weight, right? So I'll just go with here u int v as well as the weight w. So this is fine, man. So within this method, first let's go with a, or let's set the destination of the new edge. So this one will be 2. I'll just go with plus total here. I'll just go with, let me assign this one to the variable v. Now let's go with a link to previous head. So I can just go with the next of, we have considered the variable total, TOT, right? So total. So this one, let me assign to head of this one, node u actually. This is fine. Now let's update the head to this particular index. So I'll just go with head of u. Let me assign this one to the total TOT. Right. So finally, what we are doing here, we have to go or we have to store the capacity. This one edge weights of total TOT is the keyword that we have used. Let's assign this one to the weights W. Right. So we are done with this part. We are done with this part. Now let's do one thing. Let's add an edge with a reverse edge of capacity 0. This is standard for the flow, right? So I'll just go with the static here. Void, void, let me go with add. So this one will be int u, int v, as well as, let me go with a long w, nothing but the wait. So now let's go with a forward edge with a capacity w. So this one, let me go with add here, add of u v w, right? So this is fine, man. The next step is let's go with a backward edge with a capacity 0 initially. So this one, let me go with add here, add. So this is fine. So this one will be uv as well as 0. Yep. So now let me come out of this one entirely. Now let's go with a helper method to compute the parity class. So I'll just go with a when I say parity class, we will be going with the 2 bits, right? So bit 1 will be x bitwise and 1, that is shifted, and bit 0 is nothing but the y bitwise and 1, right? So let's go with the helper method. So I'll just go with static int. Let me give some random name here. Let me go with o itself. Yeah, so I need one parameter, so I'll just consider I itself. So now let me return here. Let me return. So let me consider x of i, x of i, bitwise and 1 here, bitwise and 1. So this one will be left shift 1, left shift 1, or so this one will be y of i, y of I. So and again bitwise and 1, bitwise and 1. Yep, this is fine. Let me come out of this helper method entirely. Now let's write the BFS as well as the DFS helper methods, right? So let's go with the BFS just to build the level graph for the Dynamic, level graph for the Dynamic, if you know the Dynamics algorithm. So I'll just go with static boolean here. So let me go with BFS. This is fine. So within the BFS helper method, let's reset the levels to -1. -1 in the sense if it is unvisited, right? So I'll just go with arrays here. Dot fill. We have to fill this one with the dependency also -1. Yep, this is fine. If it is not visited, basically unvisited. If it is unvisited, right? This is fine. Next, let's go with a queue for the BFS. When I say queue for the BFS, I can just represent in this way. Queue actually. So we are dealing with integers, which is of type integer. Let me consider variable q. New. I'll just go with array dq. So this is fine. Let's make use of the dq itself. Yeah, not the normal q actually. Let's make use of the array dq instead. So this is nothing but the q for the BFS. Next, we'll be going with the dependency of s. So this one will be 0. This one will be 0, right? This is nothing but the level of source is 0 initially. Initially, level of the source is 0. Source, we will be starting from the 0, right? Level of the source is initially 0. We have to go with this one. We are going with the DFS, right? Initially, level of the source is 0. Next, we have to enqueue the source. Add the source. Enqueuing means adding, right? So next we have to enqueue the source. So I'll just go with q dot add of s. Simple BFS. Now let's go with a standard BFS loop. If you know the BFS, this one, what do we call? BFS algo, right? So we'll be going with the BFS standard loop here. When q not empty, I'll just make use of is empty helper method here. This is fine. Now within this helper method, within the helper method, this one BFS helper method. So first we have to pop the front BFS, right? So this one we have to pop the front into equals. Let's make use of the poll operation that is provided by the Q actually. This is fine. Yep, this is fine. Next, let's go with the iteration part, meaning we have to iterate the edges from u, right? So let me make use of the for loop here. This one int I equals head of u, I not equal to 0, I equals next of I equals next of I. So this is fine. So within this for loop, what shall we do? Let's go with a edge destination. Edge destination. So this one will be int b equals 2 of I. Yep. Next, if the capacity is greater than 0 and not visited, then we have to set the level and enqueue. First, let's consider the if condition when capacity is greater than 0 and not visited, right? So I'll just go with if here, edge weight edge weight of I we have to consider for loop I this one. If it is greater than 0 and dep of v vertex. So if it is not visited, we are considering, meaning if it is -1, if it is equivalent to -1, then we have to set the level. This one will be dep of v equals dep of u, this one plus 1. Yeah, we are just setting the level here. Next, we have to enqueue, meaning we have to add here q dot add. What we need to add here? Vertex v, right? So this is fine. Now let me come out of this one entirely. Yep. So we have to return whether sync is reachable in the level graph, right? Whether sync is reachable in the level graph or not. So I'll just go with the return here. So this one will be dep of this one. What do we call? T actually. dp of t not equal to -1, not equal to -1. Yeah. So let me come out of this one entirely. Now let's do one thing. Let's go with the DFS to send the flow in level graph. Nothing but Dynamic blocking flow, right? Dynamic blocking flow, right? So we are done with the BFS part. Now let's start with the DFS. Right? So I'll just go with long DFS. Let me. I need the this one node u actual as well as the in, right? So I'll just go with long in here. So this is fine. So within the DFS helper method, first, if at sync, if at sync, then we have to return the flow that is pushed. Meaning, if the value this one u, if it is equivalent to t, then what we need to do? We have to return in that case, right? Yep, this is fine. Next, let's go with the total flow that is pushed from this call. Actually, I'll just go with the variable out. Let me assign to the this one value 0, initialize to value 0. Now let's iterate using the current edge pointer algorithm. This one current edge pointer. Basically, I'll just go with int I equals. So this one now of u. This is fine. I not equal to 0 and greater than 0. I equals uh next of I equals next of I. This is fine. Now within the for loop, what shall we do? So let's update the current pointer. Important for the, this is very important for the performance actually. So I'll just go with the now of u. Let me assign this one to the I. This is fine. So after this step, we have to consider the destination node as well. I'll just assign the v this one to of I. This is fine. After considering the destination node, we have to skip if no capacity, right? So if no capacity, then we have to skip. So let's write the if condition for that. If edge weight of I, if edge weight of I, if it is equal to 0, this is 1, or DEP of vertex V, this one, if it is not equal to DEP of U plus 1, yeah, then it doesn't have capacity, then we have to skip. I'll just make use of the continue keyword here. This is fine. Now let's try to push the minimum, nothing but min of available comma capacity, right? So let's recurse in simple terms. So I'll just go with long f equals uh, dfs of v comma mat dot min here, mat dot min of in comma edge weight here, edge weight of I, edge weight of I. This is fine. Yeah. So let me come out of this one. Sorry, not come out of this one. Let's move on with the further things. So what if some flows was pushed actually, in the sense if f is greater than 0, what if some flows are pushed actually? Then what we need to do? We have to reduce the forward capacity, meaning edge weight of I. Let's give edge weight of I minus f, I minus f. This is fine, man. Next, let's increase the reverse capacity, nothing but I to the power of 1. This sorry, I XOR 1 toggles the pair here. Let's make use of the XOR here, right? So edge weight here, I uh, this one, we are making use of the XOR here, right? So XOR, so I'll just go with 1 equals edge weight of this one, I XOR 1 uh, plus f actually, plus f here. This is fine. The next step is we have to decrease the remaining to push. We have to decrease the remaining to push. I'll just give here in equals in minus f. So I'll just give in equals in minus f. The final one is let's accumulate the push flow. So this one will be out equals out plus f, out equals out plus f. So let me come out of this one entirely. So we have to return the total pushed, meaning we have considered the variable out. So let me return out here. Let me come out of this one entirely, man. Now we are done with the most of the things. Actually, we can move on with the this one main method actually. Yep. So let me give here public static void main. This is fine. Also, let me remove this. Along with it, let me include throws exception. Yeah, we need this one. So within the main method, let's make use of the buffered reader and the print writer along with the n. We have to read the number of tents, right? So for that, first one, this one actually, we have to read the first line, this one 5. Yeah. So this is completely related to the input output. Let me copy paste this one. Yeah. So I'll just come here. Let me paste it over here. Yeah. So here I'm making use of the buffer reader and the print writer. So fast input, fast output. Also, I'm going with the n here. N is nothing but the first line. Basically, what is it? We have to read the number of tens. So this is the number of tens, right? 5. This one 32. We have to read this one in the input. So uh, we are successful in it, right? So let's move on with the further steps, man. Next step here would be we have to go with the source index, right? Source index in the sense after n in part nodes, right? And also we have to go with the n out part nodes, in part nodes as well as the out part nodes we have to consider. So s equals here n I can give n plus n plus 1, n plus n plus 1. Also, let's go with the sync index, nothing but here t equals n plus n plus 2 here. This is fine. So now let's do one thing. Let's move on with the iteration part. So this one will be int for int I equals 1, I less than or equal to n. So this one will be I plus plus. So within the for loop, let me go with the string here. Let me go with the string p. Uh, this one equals buffered reader dot read line. So this is fine. Dot split. So this is fine, man. Yeah, this is fine. Yeah, we are just reading xi, yi, and wi. X, y, and w, nothing but yeah, x, y, and w basically. So we have to store, now we have to store x, we have to store y, and we have to store wait wi, right? Store xi, yi, and wi, nothing but x, y, and w. So let me copy the same thing, man. Here we'll be making use of same thing right here. So instead of n, we'll be going with the xi. So this one, I'll just paste this one over here 3 times. So this one will be, let me go with the x of I, and let me go with here y of I, and let me go with here w of I. So this is fine. So this is integer dot parseInt. This one buffer data dot readline is not required, right? So this one I'll just give here. Instead, I'll give p of 0. So this one has to be p of 1 and this one has to be p of 2. Yeah. So this one will be p of 1 and this one will be p of 2. Yep. So this is fine, man. Yeah, this is fine. And yeah, so let's go with the node splitting, man. It's from node n to the node out. So we have already written the add helper method. So I'll just make use of it. So let me pass the parameters. What are the parameters that we have? So I can just check I plus n as well as weight value of I. This is fine, I believe. Yep. Now let's write the simple if condition. If parity class is equivalent to 1 comma 1, then O is equivalent to 3. That is O is equivalent to 3, right? So I can just write it in this way. See, if O of I here, so this one, if it is equivalent to the 3, then let me make use of add here. We have already written the add helper method, right? So I'll just go with si comma si comma, right? So this is fine, man. Same thing. Let me copy the same here. Let me paste it over here. So this one, if both I, this one is equivalent to 3 again. So this one has to be parenthesis. This one has to be parenthesis. Yeah. So this is fine. Of I equals 3 plus 3. Then we are going with add SIO. So this will be I plus N. So this one will be T. Mm, T and this one. This is fine. Yep. So now let me come out of this one entirely. Now we have to add the adjacency edges that encode forbidden parallelogram constraint. So this is the very important step. This itself we have to do, right? So now let's do one thing. Let me write this one quickly. So I'll just go with for loop here for uh, int I equals 1, I less than or equal to n. So this one will be I plus plus. So within the for loop, one more for loop. So this one will be j equals 1, j less than or equal to n. So this one will be j plus plus. So within the two for loops, what shall I do? Let me go with a simple if condition. If mat dot absolute, so this one of x of I minus x of j minus x of j. This is fine. Mm, j plus I'll just go with mat dot absolute here again. So this one will be y of I. This is fine. Y of I minus y of j. We have to go with y of j. So this is fine, I believe. Y of I minus y of j. If it is equivalent to 1. So if it is equivalent to 1, then what we need to do? We have to go with the parity classes for I and j. So this one, I'll just go with a new variable name OI. So this one will be, let's go with O of I, comma, OJ. This is equivalent to O of j. This is fine, I believe, man. Yeah, we are just going with the parity classes for I and j. Now, these correspond to the allowed directed adjacent steps around a 2 into 2 block, right? So let's write the simple if condition again. Let's see whether this works or not. Yeah, so I'll just go with a simple if condition here. If OI, it is equivalent to the 3, and if OJ, if it is equivalent to the value 1, hmm, or so this one, let me go with OI, if it is equivalent to 1, and this one OJ, if it is equivalent to 0, 0, or this one, what do we call OI, if it is equivalent to 0, and this one, let me consider OJ, if it is equivalent to 2, then what we will be doing here? So then let's connect the this one I out and j in with infinite capacity. We have already written add helper method for this, so I can just write it in this way. If add I this one plus n, this is fine, j comma we go, right? So this is fine. Let me come out of this one entirely. We have written the main logic actually. Yep, this is fine. Now we need the resulting variable to store the result, right? So I'll just keep result. We actually have to count. Let me initialize this one to 0. Next, result initially. Let's go with the result initially total sum of all weights actually. For I'll just go with this one for loop here. In I equals 1, I less than or equal to n. So this one will be I plus plus. So as I've said, result equals result plus W of I. This is fine. Yep. Now let's go with the Dinix max flow loops, right? So let's call the BFS here. So let's go with the Dinix max flow loop. Nothing but we will be subtracting the maximum flow from the total weight. We will be subtracting the maximum flow from the total weight. Yeah. So let's consider while there exists an augmenting level graph meaning here. So I'll just go with while of this one BFS. While of BFS. So this is fine. So within the while loop, what shall we do first? Let me copy head to the now. Let me copy head to now. Now keyword we have made use of, right? So this one I'll go with here. This one system dot array array copy we can make use of, right? Yeah, array copy. I'll just go with the head here. Head 0 as well as the now keyword. This is also fine. Again 0. Again head. Length of the head this time. Yep, this is fine. Finally, we have to subtract the blocking flow from the result, right? So this one will be result equals result minus DFS of S and O, right? So here we are making use of the Dinix algo mainly. So we are making use of the BFS and the DFS helper methods that we have written. So this one result will be result minus DFS of this one S as well as the this is fine. Yep. Now let me come out of this one entirely. We are left with only one thing. We have to print the maximum total weight of the tents we can keep. Also, we have to flush the output. So this one will be out dot println. So I'll just go with println of this one. Let me pass the result, and also we have to flush the output. So this one will be out dot flush. We have to go with out dot flush. So this is fine. Yeah. So we are done with the code, man. We are done with the code. I hope we have written the proper code. Yeah. This is pure implementation of the this one Linux algorithm, man. If you know the Linux algorithm, this one properly, you can implement this one. You have understood everything here, right? So exactly we have made use of the this one. We have exactly implemented the Linux algorithm here, right? So I hope this part is completely clear. Now, before checking the code with the different inputs or the example or with the examples, let me copy paste the signature starter template. So let me come here, let me paste this one. Yeah, let me come to the question. Let me copy this one and we have to get the output well. Let's check the same. So we have some error here. So this one has to be, uh, what happened here? So this one has to be new, keyword new, line number 29. New of, okay, let me run this one. We have one error. What? Semicolon expected. Oh, this one while I have misspelled man. Line number 55. HILE. So let me run this one now. This has to work. Oh, so we have two more errors here. So add class in the main cannot be applied to the given types. Right? So we have went with UVW. Where where actually add class in the main? So we are going with a static void add here, right? So this is fine. 1 second. Mm, so this is fine. What's wrong here? Line number 42. So this one is UVW itself, right? So we have considered UVW. Int and long itself we have considered, right? So this is fine. We are going with a forward edge with a capacity W here. And also we are going with a backward edge with a capacity 0 initially. So what's the wrong here? So oh, UVW I have given. So this is also fine. Oh, this one has to be VU. Sorry, this one has to be VU VU 0 actually. Now if I run this one, still we have the same error. Add class in the main cannot be applied to the given types. What's wrong? I'm not getting what's wrong here. 1 second. Let's clear one more. This one I cannot find the symbol U actually. Line number 70. What we have? So this one within the DFS actually. So we are going with, oh, I have given small u here, but here I have mentioned big U. So this one, let me make this one small. This error has to be gone now. So this is fine. We required intent int and we have found intent long. So we have given intent long itself, man. Intent long here. So for the W, where we considered here? 1 second. Yeah. So this one for the W, we have considered int here. Within the initialization part. 1 second here. So we are going with actually and W, right? So this one is int. So yeah, so I'm checking this one, man, this add function. So we are going with underscore at this one, right? So I have given int here instead of the long. So that is the reason it is screaming actually, I think. So this is the reason I believe. Yeah, now we are getting the output 12. So I'm checking this one from that time actually. This is fine. We are making use of this one here, fine. So we have to change the parameter. This one actually, this is of the type long, right? So I've given int. So that is the reason it is screaming. So this is fine. Now let me copy this one entirely. The output that we need to get here is 24. Let's check the same one. So yeah, we are getting the output 24. Yep, we are getting the output 24, right? 12 and 24, which are absolutely correct. So let me come to the question. Let me hit the submit button here. So let me paste the code and let me hit the submit button again. I hope all the test cases, I hope all the test cases get passed here. Just uh, let's see. It's passed. Let's wait for some time. So this is purely this problem is purely based on this one. What do we call Dinix algorithm? Wrong answer on test 3. So let's check what is wrong here. So what mistake I have done here is I have written simple if conditions here, two if conditions. So this one has to be actually O of I if it is equivalent to the 2, right? So we are going with the parity class if it is equivalent to the 1 comma 0. Then O will be equivalent to 2 actually, right? So this one instead I have given 3. So that is the reason we are getting the wrong answer, I believe. So let me copy this one entirely again. So sorry, 1 second. Let me paste this one over here and let me hit the submit button again. So that is the only thing. I believe this one actually. Instead of the value 2, I had given 3. So now this has to work. Let's see. We have again the wrong test on test 4. Let's check what is wrong here. So let's check what is wrong here. Why this is wrong? Oh, this we are getting wrong on the large inputs actually. This is expecting me output is 1 to 0 and the answer that we got here is this one. This one we are going with. Oh yeah, here we have to go with the long man. So basically, or else we will be getting the integer overflow here accordingly with the constraints that they have mentioned, right? So this will exceed this one. So we'll get the integer overflow, and for this output, that is the main reason I believe. So I hope this is the only wrong thing. Let's see. Submit this one. Let's see. I'll just paste this one. So this is 1517. Paste this one and let me copy this one and let me paste it again. Where is it? It's fine. The same problem. Let me hit the submit. I hope this works for all the test cases now this time. Let's see. I hope this works, man. So those were the two problems I believe. Instead of the this one long, I had given int somewhere here. This one instead of the value 2, actually I had mentioned 3. So those were the two problems. Running 2 on test 2. Let's see. For God's sake, yeah. This one you can see accepted here already. Running on 36. Let's wait for some time. What is happening? Why is this stuck actually? Reload this one. Yeah, here you can clearly see, man, the verdict that we have got as accepted, right? So whatever the code that we have written works absolutely correct for all the test cases, man. Again, this is pure implementation of the Linux algorithm. You have to know the algorithm to implement this one. To implement the Linux algorithm, you have to know the algorithm, right? Again, if you don't know, please do go through the graph-based algorithms playlist and you can just learn the Linux algorithm, right? Or you can learn from anyone. Yeah, that's also fine. At the end of the day, you have to understand the algorithm. You should be able to implement it, right? So this is fine, man. Yep. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.